I guess we can start.
Yep, all yours.
Okay. Hello, everyone. Welcome you to NCME Symposium. This symposium is research for practical issues and solutions in computerized multistage testing. Many practical issues arise when it comes to real-world applications. Multistage testing, in fact, require a lot of effort from designers on a number of important considerations and decisions. These considerations and decisions include assessment design, design specifications, development processes, test assembly and implementation, item pool development and maintenance, routing and scoring methodologies, test equating, test security, validity, and fairness, as well as many challenges and compromises due to competing priorities for operational implementation and applications. So all of this have great implications for practical research and operational applications. So this symposium provides an overview of many considerations of MST in practice. It would discusses many practical issues and considerations for the design, assembly, estimation, and application. It offers practical solutions for implementing operational MST from design to application for researchers and practitioners. So this symposium consists of 4 papers plus question and answer sessions at the end of the presentations. We are fortunate to have 4 well-known researchers and practitioners. Dr. April Zaneski, Professor Rick Licht, and Dr. Paul Dewsbury, and Dr. Tim David. If you have any questions, please post in the chat or ask after all the presentations. I would like to mention to you all these presentations and papers are part of the upcoming new book for multistage testing with the same title, Research for Practical Issues and Solutions in Computerized Multistage Testing. So now let's give the time to our presenters.
Thanks, Swami. It's really, really wonderful to be here with all of you today. It's nice to see over 50, maybe 60 people joining us today to talk about one of my favorite research topics, and with this amazing distinguished panel that we have here. It's been a really long summer of operational work on stuff that's not nearly this much fun. So being able to think about MST from a research perspective and prepare for this talk has been awesome. As you can see, my title today, and it's the title of my chapter in this book, is Purposeful Design for Useful Tests, Considerations of Choice in Multistage Adaptive Testing. And my co-author, my collaborator, and my co-conspirator on MST is Steve Cerisi. And the chapter that we wrote together really springs from 20 years of work that we've been doing on MST at UMass. And in thinking about this chapter and doing the work to write it, I spent a lot of time thinking about where the interest and the enthusiasm for MST comes from. I mean, we're on the 2nd edition of this book inside of 10 years, and that's credit to Duan Li and her co-editors in getting this through. And there was a couple of things that I kept coming back to and thinking about that. And I think MST is great because it's a really interesting and unique test design space to work in. If you think about the papers that, you know, from the 50s, 60s, and up to Lord's 1980 paper, talking about all the design variables. And then there's all the design research that was done at UMass. Ron Hamilton led us through that through the 90s and the 2000s. And then the consortium work with part of AICPA with Greensboro and Illinois. The LSAC did all this great work, and the AICPA did the work, and ETS. There's so much research out there on the design and all the different ways that MST, you get to make all these different choices, and you never come out with quite the same test, and you're balancing your practical constraints and your psychometric constraints, and you have all this flexibility. It's a really interesting design to be working in, and that's where I keep thinking there's this interest in this enthusiasm, and I'm preaching to the choir maybe here that you know, MST is great, but it's a pretty cool test design to work with. So. And in terms of test design, when you start thinking about MST, there's a lot of options. And test design, test development is really predicated on series of choices. And it's rare that we have a truly blank slate when we go to develop a test. But if you think about a test design on a continuum from the linear test to the item level adaptive test, the middle ground that MST occupies is really wide and really adaptive in its own way. It's an adaptable space, I guess. Steve and I were working this summer on a test proposal, and it was really fun to think about. I mean, we kind of did have a blank slate, and we were just spitballing ideas. Here's how we could do this, and maybe this, and you know, what do we do? What does this test look like? And we'll talk more about that if we get funded. But it was fun to just come up with an idea. So, aside from pandemic planning, of course. So, what I wanted to focus on is this idea of useful tests. And what I mean there are tests that accomplish whatever your measurement aims are, whatever that might be. The angle I want to impress on you today is that our research really flows from our operational work with MST, and we don't necessarily fit the traditional mold, the MST work that we do at UMass currently. But at their core, MSTs are really interesting because you could make them more or less adaptive depending on what you need. You can get more or less precision along the proficiency scale, depending on where you need to be precise. I mean, we want precision, but sometimes we need it at some places more than other in that scale. So, the perspective we took for our chapter is to think about the flexibility of multi-stage testing relative to design space and all these design options. And in our chapter, we tried to illustrate through examples what you can do differently, the different kinds of choices you can make to advance different measurement goals. So, you know, I've highlighted a couple of different tests down here, and there's the GRE that Tim and his colleagues work on. That's in the admissions context. And then you have the CPA exam, which of course is in certification licensure, PISA and PIAC, which are, I would say, assessment kind of in an evaluation space. And then the MAP CCR, which is the test that I work on in Massachusetts for adult education, and we're measuring gain over time. So whereas the other three tests are maybe, you know, measurement at a single point, we're doing pre and post testing and trying to measure gains over time. So there's different ways, you know, that MST can be used. And when you look at these 4 tests, and these are just 4 tests out of a lot of different MSTs, they're very different, but they're all functioning differently to achieve different measurement purposes. So as we wrote and thought about MST, there were kind of 3 questions that guided us to help us think through what a useful MST is. And we kind of framed it around what should my MST look like, how should my MST work, and how do I build and maintain my MST now, and then how do I keep going with this test? So first question, what should my MST look like? And you know, as someone who's contributed my share of research in this area, this is probably one of the most studied aspects of MST. Certainly Rick and my other colleagues on this panel have made incredibly critical contributions as well. And when we think about what an MST looks like, we spend a lot of time in research thinking about items and modules and stages and panels, and we've got these schematic drawings. And then if we look at those different kinds of tests, the GRE is a 1-3 test with easy, medium, and hard. The CPA exam being a 1-2, that's really focused on the higher end of your proficiency scale. So you've got medium and difficult items. and then a non-adaptive performance task. And PIAC is actually a 1-2-2 design. And then the mapped, my test again, is a 5-5-5-5-5. And I think I said 5 6 times because it is a 6-stage adaptive test with not a single routing stage in module in stage 1, but actually 5 modules in stage 1. And really what we've done, what we see here is that these are different tests with very different choices. But it's again accomplishing different measurement aims. So what does the research say when we start thinking about how, advising people or helping people to work through the research? The fancy way to say it is studies are independently informative for certain programmatic conditions, but in aggregate, the measurement results are variable. Typically, there's not really a single correct answer. And in psychometrics, I'd like to be able to give a single correct answer. With multi-stage testing, I think it just depends. It depends on what are you trying, what is your measurement purpose? What are the scores that you want to report? And then that, instead of starting at, test design at some other place, thinking about the scores and the information to be reported is where you begin and make your measurement choices for MST there. So this is just a way of thinking about all the body of research on MST designs, and it's largely focused on these kinds of things. You've got the 2-stage tests, the 3-stage tests, 4-stage tests. The 2-stage test is, 1-2 or 1-3. The 3-stage test, you get, you could have 2 or 3 branching places. That's really important if the perception and the actual need for recovery, you would do something like that. And then you can get kind of wild down below. This is where you've got 5 or 6 stages, and these are starting to approximate CAT maybe, and it might be overkill for some context. In my context, it works. So I got a lot of circles here, but thinking about all the choices, and just to return to that idea of useful tests, it really comes down to what's the result of interest. What design choices will get you there? You could choose to have more or fewer routing points and more or fewer stages, and then you have more or fewer routing points to adapt to proficiency. You could have more or fewer modules within a stage to get a better match between the examinees and the item sets. But do you need that? And it really goes back to what are you trying to do? You can choose where to put your information. Do you want that earlier in the test or later or equally distributed across the different stages? Again, it depends on what you would like to say. So this is probably my hill to die on, my horn to toot, the thing that I think I stand on I tilt at windmills maybe. But I review for a number of journals, and I often get MST themed submissions to look at. And somebody will try to do something and evaluate something about a multi-stage testing with a bank that isn't totally sufficient for what they're trying to do. And then they say that whatever their experimental manipulation was, it maybe didn't work. And I really think if your bank doesn't align to what you're trying to do, then whatever you're trying to study might not work. So it's really thinking about the item bank quality and your depth and breadth relative to what you're trying to do. And I can say from experience, like it's really hard to have highly discriminating, very easy items on, say, geometry, or really hard, highly discriminating items on functions or whatever, because there's just, there's not necessarily a lot of people up there for my pre-testing. But when you can match your bank to what you're trying to do, you can make your MST can work. I mean, it depends on how many people you have, how many, what your security requirements are, but you can do this. So you got to think about the items that you have and put your target TIFs in places where you need the breadth and depth. Do you have enough easy items? Do you have enough hard items to support your builds so that you can make the modules where you need them in whatever design that you're planning to implement? The second guiding question, the second framing question I had was really focused on how should my MST work? And there's just lots of ways to think about routing, whether you do the norm referenced or criterion referenced or information-based, number correct, all of this kind of thing here. I'm just mindful of time here. So Another choice, another example is if you have 3 or more stages, do you allow adjacent routing, which is what that graph is over on the left-hand side of the screen, where if you're in the easy, do you only allow people to go to medium, or if you're in hard, you only are allowed to go to medium or hard, or do you allow for non-adjacent routing, which typically might, in some cases, might be looked at as aberrant response pattern. In my testing context, which is adult learners, sometimes they've got some funny gaps or strengths in their knowledge. So we actually allow fully non-adjacent routing. Like if you're in the easiest module, you can go to the hardest. But it's because of the specifics of our context that we've allowed that. Then the third framing question is, how do I build and maintain my MST now and in the future? And I want to just make sure that my co-panelists have some time here, but it's thinking about test assembly in multi-stage testing. Like, how do you do that? Like there's, you know, statistical and non-statistical requirements, and those have to be conceptualized and implemented. You have to think about your item bank and having the programs to do the optimization. And then how it works, of course, is you have item selection that creates solution sets. You know, there's things like systems that Rick and Tim and others are developing that they architect really in a very sophisticated way. And sometimes, you know, there's a lower tech hand assembly that works. But again, that's just going to depend on the context that you're working in. There's some choices of how you handle security. You can conceptualize security as an inventory control process. You can integrate those considerations into assembly. Some of the key features from Tim's chapter that I found interesting to think about is how you have a mechanism to handle multiple forms, your strategies for item selection and bank usage, and how do you refresh your item banks periodically. So the few points that I've hoped, you know, and I wanted to illustrate here today, to me, design for multi-stage testing occurs at this interesting and fascinating juncture of test development and test use. And when we think about multi-stage testing, choices have consequences, like everything, I suppose. But some of the choices that you can make are going to be better for interpretation and use than others. It's really fun to work in this design space and to think about what are the parameters that are going to define your design space. What is the item bank that you have? What's the item bank that you'd like to have? What are the kinds of, where's the precision that you need in your scores? To just kind of lay out what do you want to do, and then do the research and look into the literature and evaluate options within the space that you're working in. You know, begin the conversation where test development more typically ends, I think. Oftentimes we think about score interpretation and use and score reporting at the end of things. I would say, you know, I think this is probably not revolutionary, but it should be the first part of the conversation. What's going to be reported? How do we do that? Look at the previous research, give some weight to literature that's kind of operating in the space that you're in. I mean, certification and licensure literature on MST is wide and deep. There's a lot of good stuff there. Some of that's going to be more useful in education than others, if your context is education. And then consider all those options and make choices that are right for your test. So my final slide, I just wanted to, I didn't feel like I had a lot of pictures in my presentation today. So this is my multi-stage test. So when I was talking about that 6-stage, 5 modules per stage test, this is the mapped that Steve and I work on at UMass. This is my cat, Nadia, and here's my email if you'd like to be in touch and talk about multi-stage testing or anything else. So next.
Yeah, you got unshare.
Okay,
April.
Let me do that.
Okay, hopefully this comes up here. So I'm Rick Lecht at the University of North Carolina at Greensboro, and when a lot of this stuff started out, actually my involvement in this began in about 1995. I was working on the U.S. medical licensing exam, which at that time was 600 items, and came up with this idea of applying multi-stage, knowing we could never go to an item level CAT because we couldn't do all of the test assembly at an acceptable level in real time. And so the idea is, how do you pre-build an adaptive test? And so that led to a series of papers and some other things. Now, in terms of the cast, you might wonder why I have Romeo and Juliet up there with the quote from there, what's in a name, that which we call it by any other name would smell as sweet. The simple fact is, if you go into the literature, multi-stage has been there for quite a long time. It's just called different things. Cronbach and Glesser called it two-stage testing back in 1953. Fred Lord did the Flexa level testing. We originally called it computer adaptive sequential testing to allow for both the adaptivity and other things. I still tend to call it computer adaptive testing for a number of different reasons. Adaptive testlets, computerized mastery testing. So we've sort of settled on the multi-stage testing, and of course, Dwanli and Alina's edited book, has helped to, I think, pull a lot of the research together in one spot. My own message is, basically this has matured into a delivery architecture. When we first did this there in 1995, there was no software out to build these things. Guess what? Had to write the software to actually do that, to assign forms. We did massive field tests with medical students in 1996 and 1997. And we're using, trying to look at issues, not only like the pool type issues that April alluded to, but also could people actually recognize if they're moving from easier to harder tests, dealing with number correct routing versus IRT-based information routing, where you have to have parameters on hand, score them, and then select based on max information. And so a lot of this has really come together. One of the big things, by the way, people really like, in addition to all of the good QC mechanisms, et cetera, compared to CAT, is examinees like to be able to review their items. And that's been around since, at least I remember doing surveys with this with real examinees in 1996, and that was one of the first big issues. They do not like the no review option. So, so anyhow, that's where we're at. Now, what I want to talk about is sort of four things here and give the others some time. One about this, a little bit about panel configurations, item bank issues, which April alluded to. And it turns out it's one of the biggest issues, I would agree, in multi-stage. Some assembly strategies that at least I've worked on. I'm sure Tim will have other ideas on that ETS has done. And then a few words about the system support, at least as I've been involved in that over the last 20 years or so. Little bit on notation here. I like putting the CA in there for computer adaptive multi-stage testing. And it's not to say it's anything different, but many organizations think that they need an adaptive test. They, literally, and by policy, they say, well, we've heard about CAT and we want an adaptive test. So if you put the computer adaptive multi-stage in there, they're getting it. It is adaptive. Now, a lot of the terminology we now use, panels, modules, that type of thing, actually is something that came out of radio frequency engineering. You had panels of electronic equipment, something broke, you pulled out a module that was not working and plugged in a new module. So that was really the idea, is to engineer these structures so that you could pre-assemble them. Now, many groups have opted for this simple 1-3 design that you see there, and each module is made up of some number of items, and you route from the easy, medium, and hard at the second stage. And then, as April mentioned, you can go to additional stages there. You can also have fixed panels where they're actually objects, where all the panels and routes and the items are fixed to that panel as a data object, and it becomes a self-adaptive unit. Or you can have what we call bundled MST, where you basically create a panel with the slots in there and pick the modules in real time to give you a little bit more of a randomization option. These are just some of the panels. April showed you kind of a MST on steroids, with the 6th stage and all the different levels. For practical use, we found that this covers, at least in my case, most of them I've dealt with. We've done the 1-3. Originally, we proposed doing the 1-3-3 in some of the early adaptive sequential testing type literature. And I've actually done one with a group in England, an online test that uses the 1-3-4, kind of in the middle right there for reading tests and listening tests. And as April mentioned, the AICPA, when that was designed, we went originally with a 1-2-2 to allow them to have some diagnostic information in the second and third stages. And then they just recently moved to a 1-2 design, a very simple, the simplest panel configuration. Now, a little bit about item bank issues here for MST. This, by the way, lets you see how many items you need per panel under these different design configurations. And I haven't shown you all of the panel configurations, but it's really interesting that when you put this kind of slide up and say, you know, if you really thought you wanted something like the 1-2-3 design kind of in the middle there, then we would see that if you had as many as 30 items per module, you start needing 200 items per panel. If you need 5 panels, you start doing the math. I need 1,000 items. And so it lets you do this kind of inventory up front. And it's not just item counts. These are items that will actually fit your multi-stage design. But a number of groups I've dealt with, both for alternative assessments, certification licensure, as well as K-12 education, this is the first place where we hit a stumbling block. They look at these counts and go, there's no way we have the item banks to support that. And so often they opt for a pretty simple one. Now, if you wanted to deal with item exposure, which I'm skipping over how we would get to it, but you can start to look. Here I've just got the 2 designs, a 1-3 and a 1-2-3, and you can look at 3 different item counts, 15, 25, 35 items, that say if you wanted a 10% exposure in the population, you start needing 1,400 items for the simplest design, 2,100 items, you know, and you start getting down to 1% exposure in the population with non-overlapping content, 21,000 items. So it can quickly, again, show people what to expect. They get bothered by that, but again, that's the reality. Some of the item bank limitations we have, whenever we do this, do simulations, etc., we show you pictures like this. April showed it. This is the 1-3 design. We call these MIFs, module information functions, where you have the module at the first stage and then the dashed for the next, the second stages. This is what you'd like. This is what the banks often support. And if you look at the y-axis there, the amount of information is far less than we think we'd actually want. So we often have to modify targets to meet what's in the bank simply because the bank was never built with a multi-stage test in mind. April mentioned Ron Hambleton. You know, Ron's a good friend too. And the first time I ever saw presented this type of thing, we were doing it for the medical exams, and Ron looked at the information targets that came out of the easy, medium, and hard routes, and he said, gosh, there's not that much difference between the easy, medium, hard. And again, it was a limitation of the item bank, not multi-stage. Multi-stage simply made it a reality as to what we needed to get that adaptation in there. The exact same problem exists with CAT. Most people just don't know they have a problem because they don't have the structures to look at it. So basically, if you've got a lot of data across the spectrum, you're going to need items, not only easy, medium, and hard items, but they also have to be balanced for content. That can sometimes be difficult in certain content areas. I mean, it's hard to write very easy trigonometry items in math. It's also very hard to write very difficult numbers and number systems items. If you've got passage-based items, reading set, item sets, etc., you have to decide then how much of a constraint the passage puts on the assembly process. These are real data, so you can see we're not seeing a lot of separation in the passage sets that exist in an operational bank. So it's pretty hard, since you can't split the passages up, to actually create easy, medium, hard type modules and still meet the passage content constraints that are required there. Some assembly strategies. One of the things I've worked a lot with actually one of my former students, Zhao Luo, who's also got another chapter with me in the upcoming MST book, is we call this a bottom-up design. It's what we initially did. You have separate targets for each of the modules at each stage. And then each stage usually has its own content constraint. So we formally, in the optimization sense, call it a multi-objective function, multiple constraints at optimization problem. And so you're building it out as you see below. You've got a stage 2 content, stage 1 content. What Zhao has worked out with some of his software and colleagues at the NCLEX, the NCSBN in Chicago, was actually a top-down strategy. If you can't break your content down by stage, then you actually specify content for each route and have 3 separate targets, as I show at the upper right there, sort of for the easy, medium, hard route. And then you simply put a constraint on the assembly that you have to have the first stage module share all the same items. And so you can kind of see how that appears in the left-hand little graphic there, where it's a 1-3 design, but again, you have the shared content for the modules and then separate content. This actually sets up as almost a balanced design, assembly design, and has some things in common with missing data problems in equating designs as well. Now, a 1-2-3 or a 1-2-3 panel, I actually like this one a lot more actually than the 1-3. The first module helps you split into the second stage, medium, easy, medium, hard. And then the second stage helps you make optimal routing decisions to the third stage, and you put your third stage modules where you need them most, perhaps at basic, proficient, advanced cuts, for example. And so we've got the same kind of concept there. In this case now, we've simply got 6 targets that we might want to build to. And so again, we have to ask, would we have that coverage? If you look at those targets, especially the orange, we're peaking down at about maybe minus 1.6 on the theta scale or up near 1.5. That's a lot of very hard and very easy items. You need to plan for that. This, by the way, is the type of assembly we could do. And you can actually build your exposure control almost exactly into the population. You want 10% exposure control? Well, we might get 30 or so modules where you have 10 of the first stage, because anyone who enters any panel is going to get that module. And so if you have 10 unique modules, you have a 10% chance of getting any one of those. And then you sort of split it to route people left and right at the second and third stages there. Again, do you have the content to do that? And by the way, the test assembly, if we did this with certain software, might take hours or days. If we do it with heuristic ATA software, this actually took 0.02 seconds to run these 30 modules and build them. If, again, you've got complex item sets, you've got simulations based in, the modules just become far more complicated to put together because you have fewer degrees of freedom there. So now a few words about support systems. April said a bit about this, and I know Tim will have probably more to say about that as well. Building MST without automated test assembly is like trying to build a house with a butter knife. There are some good tools out there. I think anyone who gets serious about this eventually has to modify those tools for their own use. But GLPK and LPsolve are pretty decent solvers. They don't work for everything. I mentioned one of my former students, Zhao Luo. He's now at Amazon, but Zhao wrote a package called XXIRT, which will also be explained in the new book. And that interfaces with both GLPK and LPsolve and does bottom-up as well as top-down MST builds, including a lot of content constraints. If you want to use R, there's the LP-Solve API that you can deal with. Wim van der Linden and some of his colleagues put a review out on that and showed some examples how to do the simple two-stage MST. MATLAB, you could probably run that. Cast-iCell was the software I originally did, and there's some new versions I've been doing that use a heuristic. Some groups are now moving to tools like FICO Express, which is an online optimization engine that can actually work off the cloud. And then there's also CPlex and some other tools out. But again, pick one, kind of build the systems around it. For this kind of design, you need to think about the operational pieces. If you're going to have like the 1, 2, 3 at the top left here, you've got multiple panels active. If somebody's seen any of the modules before, you may need to filter them out. Create, if you're doing numbers correct score routing, you have to create routing tables beforehand. A lot of pretty complicated systems design work underneath. The bottom right is how that ATA problem sets up, where you've got the content as well as statistics going into building all of these. And then again, the operational system is basically at the lower left in terms of a functional specification of what you need for those systems. Again, this is just, I'm not going to go in detail through this, but these are the kinds of design plans you need to work out. You just can't say, well, let's do MST. Somebody's got to build the data structures, et cetera, to interface with the pool, ATA, building the forms, getting those to work with whoever your test delivery vendor is, to be able to make sure that they can support those structures, the routing, et cetera. The panel assembly, again, looks kind of like this then. If you are doing the routing, you've got that type of a basis. This is doing, again, the 1, 2, 3 design. But again, you may need to build a system to build the modules first, and then mix and match the systems, the modules to build the panels, and then actually QC them, maybe do some audits, et cetera. So the bottom line, it is a very complex thing. The good news is we've got some experience out there now. So I'll turn it over to you, I guess, Paul. I'll stop my share and you can take it from there.
Okay, thanks, Rick. Let me just share my screen now. So I think we're almost perfectly on time, so I'll try to keep us on time. My talk is on item calibration in multi-stage tests, or more specifically, sharing now. So my talk is on item calibration in multi-stage tests, or more specifically, item calibration in data generated by MSTs. There's a little change in attitude. It's about analysis as opposed to design from the last couple of presentations. Okay, so whenever I talk about whenever I talk about item calibration in MST, the first question is, why do we bother? After all, a lot of MSTs use pre-calibrated item parameters, and often in order to design the MST in the first place, you usually want to have existing item parameters. So although it's possible to use pre-calibrated item parameters in MST data calibrated from unadaptive data, there's several reasons why estimating item parameters MST data can be beneficial. Firstly, you may have more data in the MST than you do have in the pre-calibration data. And this is particularly the case for large-scale assessments such as NAEP and PISA. Secondly, the pre-calibrated item parameters may not fit the MST data, so there could be contextual or position differences between the items in the pre-calibration and MST assessments. Also, there could be just simply differences in the true population item parameters between MST and non-adaptive administration of the same item. Thirdly, you could have new items introduced directly into the MST assessment after you've already transitioned to MST, and so you might simply have simply may not have the capacity to calibrate the items in non-adaptive data. And then finally, it's a little intuitive, but if you're not capable of estimating the item parameters in MST data, there's less methods available to evaluate the fit of the item parameters in MST data. So the challenge of item calibration with MST data as opposed to item calibration with non-adaptive data is that MSTs and other adaptive tests involve multiple test forms that differ in difficulty. Therefore, each test form must be equated in some way to ensure valid item calibration across forms with different difficulties. And it's been observed that some standard equating and item calibration procedures when applied to MST data don't actually work very well and produce systematically biased item parameters with respect to the module, and those biases are large enough to have non-negligible effects on proficiency estimation. So we argue along lines with several other authors that item calibration in MST is best thought of as a missing data problem. And the application of missing data theory in particular from Rubin can be used to ensure valid item calibration in MST data. So when I say missing data theory from Rubin, I'm going to very quickly go through the basic idea that he comes up with. Firstly, he notes, Rubin notes that the default likelihood in marginal maximum likelihood, and it's related also to Bayesian inference, ignores the missing data process. So this is the individual level likelihood in IIT convention. It's probably a fairly familiar equation for a lot of people. We have the likelihood of beta, the matrix of item parameters, conditional on the y obs, the vector of observed item responses for person I. Theta I is a proficiency for person I. P is a conditional probability, and F, theta I, is the density of theta I. So the default likelihood that people will use by default in their programs ignores the missing data process. So the fact is the actual likelihood accounts for the joint probability of observed item responses in the missing data pattern. The point from Rubin is that we didn't only observe the item responses, we also observed the missing data pattern. And therefore, the actual likelihood accounts for the joint probability of both the item responses and the missing data pattern. So the actual likelihood could be written like this, where you have the joint likelihood of beta and phi, where phi is a parameter that governs the missing data mechanism, conditional on y obs and the missing data pattern. Y miss is the vector of missing item responses for person I. So these are the responses that would have been observed if the student answered all of the questions. So in the context of MST, these missing responses are the responses to the modules that the student was not assigned. Not that the student intentionally missed it, but they never had an opportunity to respond to it, so their responses are missing. And then MI is the vector of missing data indicators, or the missing data pattern. And Rubin shows that the actual likelihood and default likelihood are proportional in special cases, but not always. And when they're not proportional, there's no guarantee that inference or the estimation of item parameters in this context will be accurate. So as many people know, probably the most important criteria to ensure the default likelihood is proportional to the actual likelihood, so you get the correct inference, is this assumption of missing at random. So the missing at random assumption states that the missing data pattern, MI, is independent to Y miss, the missing responses, conditional on the observed item responses. So essentially, intuitive way of thinking about it is the students that are missing on a particular item equivalent to the students that are missing on that particular item, conditional on what we know about them. And it's been shown that missing data in MSTs is missing at random. We know what makes students that have different routing decisions different because we made them different. We routed them in different ways. And therefore, MML item calibration is valid for MST. But I've added in this kind of qualifier, simple MST, because often these proofs are assuming a particular type of MST. An MST where the missing data probabilities depends only on the item responses. And it's important to make that qualification because many MSTs in practice are not actually simple MSTs. A lot of MSTs in practice are not actually MSTs according to these previous research, and missing data may not actually be missing at random. So it's important to understand in which ways MSTs can differ from simple MSTs, and what that means in order to properly account for the missing data. So in order to kind of understand this and to recommend what sort of procedures we should be using for item calibration, I've defined 5 types of complex MSTs. And these definitions are with respect to the implications from missing data theory. So the first type is entangled multidimensional MSTs, second type non-entangled multidimensional MSTs. I'll define them in the next couple of slides. The third type is when you use contextual information as part of the routing decisions. The fourth type is when you have non-random assignment of the first stage module. And the fifth type is when you have MST only provided to a subset as opposed to the total sample. To illustrate these MSTs and simplify the notation, we'll just consider a 2-stage MST where the first stage routing module, ROW, with first stage routing modules, ROW, denoted by ROW, and second stage target modules denoted by TAR. So an entangled multidimensional MST is an MST that has routing decisions that are derived from an entanglement of responses to items from multiple subscales. So to be a bit more concrete or mathematical, we have the conditional probability of the missing data pattern on the second stage is a function of the the missing data pattern on the second stage for a given subscale is a function of the item responses on the first stage for all of the subscales. So an example of this is some NATE pilots that were administered a few years ago, where the routing was based on an EAP score calculated from item responses across all subscales in the first stage module. And that determined which second stage module a student got, but that second stage module had multiple subscales. In this case, ML multi-unidimensional item calibration. So this is the most common procedure for item calibration with simple structure multidimensional data is not valid for entangled multidimensional MSTs. And this is because all of the subscales are important in terms of determining the pattern of missing data, and therefore it's important to model the probability of all of the subscale items on the routing block, on the routing module simultaneously in order to ensure that you properly accounted for the missing data. And we also showed that ML multidimensional IIT, or MERT, which does simultaneously account for the probability of all of the routing items, is valid for entangled multidimensional. Non-entangled multidimensional MSTs are just defined as essentially the opposite. We still have multiple subscales, but the routing probability to later stage items of a given subscale only depend on item responses of the same subscale. So in this case, we have the conditional probability of the missing data pattern on the second stage for a given subscale is a function of the item responses on the first stage for that same subscale and no other subscale. In this case, MML multi-unidimensional item calibration is appropriate in order to account for the missing data. It's also true that MERT is also valid for missing data, and so you might prefer one or the other for different reasons, but they're both appropriate for accounting for the missing data. The third type is contextual information used in routing. So these are MSTs that use contextual information such as characteristics of the test takers, the routing decisions in addition to item responses. So we have the conditional probability of the missing data pattern on the second stage is a function of both the item responses on the first stage as well as xi, where xi is a vector or scalar of contextual information. So the contextual information could take the form of a prior test score used to improve the accuracy of routing. Alternately, routing probabilities could depend on demographic information to ensure a better balance of exposure of items across demographic groups. So this is something that's recommended by Chan et al, and it was implemented in PIAC. So the routing probability is conditional on the responses to the routing were different depending on the native language speaker status and the education level of the person. So these are contextual information that have been used as part of the routing, and that has missing data implications. So when you have contextual information collected independently to the item responses that have been used in the routing decisions, you can account for that by the use of an IIT latent regression or a multi-group IIT, depending on the nature of the contextual information, in particular, whether xi is a continuous variable or a categorical variable. But it is important to account for that variable that you've used in the routing that you've used as a determinant of the missing data pattern in order to properly account for the missing data and avoid biased item parameters. The next type is non-random assignment of routing modules. So MSTs with non-random assignment of routing first stage modules are defined when the assignment of the routing module depends on some external variable. You have the conditional probability of the missing data pattern on the first stage here is a function of xi, some external variable. We also have the conditional probability of the missing data pattern on the second stage as a function of the observed responses on the first stage, as well as xi, this external variable. So these designs are talked about with other names in the literature, so they may be referred to as targeted MST designs. An example of a targeted MST is the MAPT CCR that April talked about. And finally, if the contextual information is a prior test score, the design may be referred to as a longitudinal MST. But for the purpose of missing data, we don't need to make a distinction. The missing data may be modeled by employing a multi-group IIT, where each group corresponds to the set of test takers with the same assignment of first stage modules. There are other ways to account for xi, but we think that this is the best way to account for the missing data while having the weakest assumptions as possible about the distribution of xi. And the final type is MST assigned only to a subset of the sample. So some MST designs, in fact, only provide the adaptive assessment to a subset of the test takers, while others receive a non-adaptive assessment. So I'll skip that. That's a bit more complicated to describe, but examples include PISA and PIAC, where a proportion of the test takers, depending on their countries in PISA or depending on their computer familiarity in PIAC, will not actually be given the MST, but instead will be given a non-adaptive paper-based test. And that obviously affects their missing data patterns, and so that has implications on item calibration. So in this case, we recommend a multi-group IIT model again, where one group comprises test takers receiving the MST and one group comprises test takers receiving the alternate test. So I've got a few minutes left. I did a simulation to illustrate these recommendations and confirm these recommendations, given that there's 6 designs and 2 methods. The default method as well as a recommended method for each of these designs. It's quite a complicated simulation, so I won't be able to describe all of the details about it. But quite concisely, I'll just describe what I think are the most important. We simulated a 2-stage MST with 2 modules in the second stage, easy and hard, and 1 or 2 modules in the first stage, depending on whether or not there was non-random selection of the first stage module. Routing was based on total sum score, but for the purpose of missing data, whether it's sum score or EAP or MLE doesn't actually matter a great deal. In the unidimensional designs, proficiency was simulated in this way with respect to xi, the contextual variable. It was simulated with these parameters to have a mean of 0, standard deviation of 1, and an R squared with xi of 50%. In the multidimensional design, again, we have a mean of 0, standard deviation of 1, and a large correlation of 0.9 between the subscales. The item responses were generated from the 2PL IIT model. All of the discrimination parameters are the same, but you can't stop me from calling it a 2PL model. And the intercept parameters are different, obviously, depending on the module, given that's the point of MST. For each MST design, 1,000 simulations were conducted with 5,000 simulees each. So they're relatively large calibration samples. So as I mentioned, we simulated for each of these designs and then used the default procedure as well as a recommended procedure, the numbers of biases. The numbers in parentheses are root mean squared error. And because the biases are typically the same for all items within a module, I've just averaged across all of the items within each of the modules. And I'm running out of time, but you can see that the default procedure, in all of the cases where the default procedure and the recommended procedure was not the same, everything except the non-entangled multidimensional design, there was a notable bias with the default procedure and large root mean squared errors. Whereas for the recommended procedures, there was much smaller biases and much smaller root mean squared error in each case. So in conclusion, while missing data due to MST routing is ignorable with the default likelihood in MML item calibration, in practice, many MSTs are a little bit more complicated than the ideal MST in the literature, and it's not always ignorable with the default likelihood. So we kind of came up with a system of classifying complex MSTs and then recommended procedures with respect to these complex MSTs. Thank you. So I'll let Tim go ahead.
Thank you, Paul. Can people hear me?
Yes.
Ah, excellent. How about this? Can they see what I'm presenting?
Perfect.
All right. Well, I have to say just at the outset that if this is the new normal, where I'm presenting here in my pajamas in my Barca lounger, I'm all for it. Bring it on. I'm ready. But I'm talking here about evaluating and predicting MST performance, and a lot of this builds on some of the things that you've seen in the earlier presentations here. In that, let's see, how do I? Can't seem to go forward. Doggone it. There we go. So why? Now we've gone too far. Why predict test performance? And I'll say that it's often useful to predict how a test will perform prior to it being administered. And why do we do that? Well, we do that to confirm that the test has been properly designed. We've done this for decades, in that when a new test is being developed, we wonder, is 30 items for this test enough to give us the levels of reliability we want or need, or do we need to extend it to 40? So we've always tried to sort of project or predict how a test will perform before we administer it. Now, you don't know for sure how anything is going to work until you actually get it in front of live examinees, but it's useful to predict these things ahead of time. Second reason is that we'd like to confirm that a particular test form built to a particular set of design specifications has been properly assembled. And in Rick's presentation earlier, he showed us some things that you'll see examples of here, where it was sort of evidence of whether the assembly process was able to meet the targets it was issued. So that prediction is fairly straightforward for conventional tests, non-adaptive tests, because the connections between item performance and test performance are pretty direct and well understood. So that, for example, if we've got a test comprised of items with an average p-value of 70, we would expect that once we administer that test, the mean score will be about 70% correct across the examinees who take it. Now that assumes that the item statistics, the things we use to characterize the items, have been estimated from essentially our target examinee population, so that there's some level of consistency there. Things are not so simple with adaptive tests like MSTs, because here performance depends not just on the item characteristics, but also on the logic that routes examinees through the test, so that we could take the same exact MST panel, the same routing test and say second stage tests, and vary the routing rules and get very different levels of test performance, so that our predictions are specific to the logic that we'll use when that test is administered operationally. So let's start with a listing of the metrics by which we'll evaluate performance. Some of these are directly observable, and by that I mean that we don't need to make a lot of inferences in order to evaluate these. They're sitting there right in front of us once we have assembled an MST panel. The first of these is the extent to which our assembled panel meets the content constraints to which it was assembled. And our display for evaluating this is a simple table like this that shows the constraints there, the target values of numbers of items in each of these content categories, versus the number that we had actually achieved or observed once we had assembled our form. So that this is basically just an evaluation of whether our test assembly process met the constraints in which it was responsible for meeting. A second similar thing is the fit to the statistical assembly targets, and we saw a lot of these in Rick's presentation earlier. So that this was the observed module information functions. The targets are not shown here, but ordinarily you would show what you got versus what you wanted, and use that as a means of determining whether your assembly process or your assembly pool are both sufficient to meet the targets they're given. So now let's move on to some metrics that are inferable, and by inferable I mean they are estimatable or projectable, given both item characteristics and the characteristics of your target examinee population. So the first of these is score distributions. What sort of score distribution do you expect your test to return? And you can learn a lot about a test from the distribution of scores. Here's a nice distribution. Looks beta binomial to me. It looks like the test is appropriate in level of difficulty for the examinees that we expect to take it. It's not skewed in either direction. That would be a sign that your test is too easy or too difficult for your population. It's not sharply peaked in the middle. That might be a sign that your test is not discriminating as well as you might hope it would. So that, like I say, there are few things that are more informative about a test functioning than the distribution of scores that it returns, or in this case is expected to return. You can get a more detailed picture of the test measurement properties through the conditional standard errors of measurement. And these look like this, where the solid line is essentially the standard deviation of the error in the score estimate. The dotted line here is the expected ability distribution. So that this is again a test that looks like it's doing its best work over the region of the score, the performance range where most of our examinees are expected to be located. Third thing we can look at are what are the routing rates and what are the routing error rates. So the routing rates, here they're shown conditionally. This is for a, again, for the simple 1-3 design that ETS seems to strongly prefer. So that the lines here are the conditional probabilities of examinees at any given proficiency level being routed into either the easy, the medium, or the hard paths. So that you can see that to the left of -2, your probability of going on the easy path is virtually 1. To the in the center, you've got it. That's where decision needs to take place, and you can see that the middle route, the dotted one here, does its work only between, say, -1 and +1. Here are the corresponding routing error rates, and again, where we're making decisions, that's where we'll tend to make our errors, and our routing error rates tend to be highest at the routing decision points. But fortunately, if those decision points are located at the crossing points of our module information functions, the consequences of those routing errors may be negligible. In that the wrong route that you were sent along may be just about as informative as the right route that you should have been sent along. So there are other metrics that are certainly possible and probably advisable in a lot of situations that provide a deeper look at MST performance. Some of these are predictable prior to administration or inferable prior to administrations. Others become possible for review only after administration. So the first of these is score bias due to incorrect routing. And the second is sort of related to that, which is sort of the robustness of reported scores to unusual responding, and that incorrect routing decisions are often the result of examinees who, say, start slow, or who feel some sort of pressure and don't perform at their best at the outset. And we've always sort of maybe fictitiously sold adaptive testing as self-correcting, and it's really not. In that adaptive testing doesn't allow a slow starter to recover and end up where they should have been, any more so than doing poorly on the first half of a conventional test does. That doing poorly during any section of a test puts limitations on your ultimate score, unless the test is of essentially unlimited length. So that where we become maybe concerned with MST in particular is that some of the easy second stage module probably doesn't allow students, puts limitations on the ultimate score a student can obtain, even if they get all of the items in that second stage module correct. So that in extreme cases, there is some sort of, call it bias, that is the result of an able student being incorrectly routed to an easier module. But that's not necessarily the fault of either the routing logic or MST in general. It is a reflection of the fact that the student did poorly during at least the first portion of the test. We certainly know that some scoring mechanisms are more or less robust to unusual or non-model conforming responses. So that's what I mean by robustness to unusual responding. And these are things that you wouldn't necessarily evaluate each time you put a test form together. but you know, things that might be looked at during the design process. These last two things are things that have to be looked at with real data post-administration. These are test timing and speededness. You know, one of the things we get very concerned with adaptive tests given under time constraints is whether the hard items given to able examinees are putting them under more time pressure than the easy or items given to struggling examinees, in that a lot of adaptive tests are speeded in exactly the opposite direction that conventional tests tend to be speeded. So that is certainly something that that ought to be attended to during the design process. And the last thing is item model fit. You know, do the item parameters that we've estimated in advance and assumed during the administration and scoring process, do those in fact fit the data as it's presented? So how do we go about predicting MST characteristics? Well, we'll talk about two approaches here. The first of these is the old tried and true simulation. The second are a pair of analytical approaches as alternatives to simulation. And what we'll talk about predicting here are basically what I'd call the inferable test characteristics. So those are things like score distributions, conditional standard errors, and routing probabilities and routing error probabilities. So that all of these approaches work, as presented here, work conditionally, so that they, and the key to all of this is the generation of essentially conditional score distributions, which are distributions of observed scores conditional on a single value of true proficiency. So that we define that grid of proficiency values. Under simulation, we use the IRT response probabilities to simulate the administrations of large numbers of MSTs at each proficiency level. And from those conditional distributions, we can read off almost everything, in that the variance of the distribution of observed scores conditional on a true ability value. Well, that's essentially the square of our conditional standard error of measurement. From those conditional distributions, we can determine directly the proportion of examinees at a given true proficiency value that will have observed scores that exceed or fall short of each of the decision thresholds. So that will give us our routing probabilities. We would also know how many of those routing probabilities are in fact correct or incorrect. We can then take those conditional results, if we choose to, and aggregate them up across proficiency levels, weighted by the assumed population distribution of proficiency, so that we can take those ability conditional score distributions and sum those up, weighted by the examinee proficiency distribution, to get an aggregate or a population score distribution, total score distribution that looks like the one we showed earlier. So what are the advantages of simulation? Well, it's simple. It ought to be. We do enough of them. The drawbacks, the first of these may seem an odd complaint given the state of today's technology. It can be time consuming, to simulate tens of thousands of examining records doesn't take very long. But I was working was it last summer or the summer before, a couple of years ago, with a young man named Huang Yu Lim, who's got another chapter in Duan Li's book. And he was, taking sort of the first presentation, April's presentation, where she was looking at sort of design space and what works well given certain circumstances. Well, Huang Yu was looking at sort of parameterizing that design space and optimizing the design over it. So he took and put together a quick automated assembly routine, like Rick was talking about, with the quick methods of evaluation that we'll talk about in a minute, the ones that are based on analytics rather than simulation, and essentially simulated, well, millions and millions of tests, each built to slightly different design specifications, and was looking, searching the design space for an optimal design given a particular set of items, a particular assembly pool, so that in his application, sort of cutting a few seconds off of a simulation and doing it essentially instantly by the analytical method was turned out to be important. Second drawback to simulation is that it can be imprecise, especially if it's done quickly with relatively small samples. And you see that particularly with routing and router error rates, because some of those are based on very low probability incidences, so that you may have one or a handful of examinees at a fairly low proficiency level who in simulation do well enough to be routed along the highest route, so that the curves that I showed earlier, those guys, are not nearly as smooth. These were done analytically by the procedures we'll talk about in a minute, rather than simulation. But the simulation-based curves here look very rough, particularly in the tails. So what are the analytical approaches? The first of these here is based on large sample theory, and that's just the assumption that the distribution of theta hat given theta as an MLE is normal. That it's listed here as unbiased. We know that it's biased, but fortunately we know what the bias is, so that we can build that into to our simulation or to our analytical results. And I've done that in what I'll present here in a minute. And we know that we assume that under large sample theory, the variance of the ability estimates is related to the information of the route along which the examinee went. So we can use this again to create these conditional score distributions, and from those conditional distributions, routing rates and error rates, the test level conditional standard errors are estimated essentially as weighted sums of the route conditional standard errors with the weights given by the routing probabilities. So the advantages of this approach is that it's fast and easy, fairly general, instantaneous, essentially. It does make the strong assumption that MLEs are in fact distributed like MLEs are supposed to be distributed. So how does it work? Does it work? Well, here are CSEMs based on simulation. Those are the ones with the dotted line, and based on the asymptotic analytical approach. And we can see that across the bulk of the performance range here, they're in pretty close agreement. As experience has led me to expect, the analytical results are a bit optimistic in the tails, in that the examinees in the extreme there, even simulated examinees in the extreme, don't quite meet the requirements of our MLEs. That don't meet the assumptions of our MLEs, which of course are based on very long tests. So that it's not a terrible fit here, but it's not an ideal one either. Like I say, that asymptotics are almost always on the optimistic side. So that leads us to our second analytical approach here, based on a recursive algorithm. And I don't know how many years I've got left in me, but I can think of a worse way of spending them than serving as a tireless advocate for use of the Lord Wingiersky recursion. It is in my opinion, the most, maybe the greatest and most underappreciated accomplishment in the field. But anyhow, that Lord Wingiersky found a simple recursion that allows you to exactly compute the number right score distribution for, conditional on a given true proficiency level, so that it's not approximate. It's not based on, well, it's based on the usual IRT assumptions, but it's not based on large sample theory. But it that if your item response probabilities are right, it gives you the correct distribution of number right scores. Well, there are a lot of MSTs, GRE chief among them, are essentially scored by equated number right scores. GRE is not scored by an MLE, in that their studies of, well, the robustness that we talked about earlier showed that that number right scores are a bit more robust to unusual responding than MLEs are. So that the GRE and other MSTs are scored by essentially conventional number right or point totals that are then IRT equated. So that given that sort of scoring, you can compute all of the performance metrics that we talked about earlier exactly, without making the sort of large sample assumptions made by the previous approach. So again, it works just like the large sample approach, except that the conditional store distributions are computed directly from, are computed exactly rather than approximately. It's, again, fast and exact, instantaneously. It is restricted to equated number right scores, in that the performance of equated number right scores is not equivalent to the performance of MLEs. In our experience, if everything is on the up and up, MLEs, which take advantage of pattern information, may work a little bit better, but with real examinees responding under real conditions where you've got error in your item parameter estimation, the equated number right scores work as well and sometimes better. They're a good deal more robust. So again, how does it work? Well, it's exact. It's not a case here of the recursive algorithm converging to the simulation. It's the opposite. The simulation has to converge to the recursive algorithm, because the recursive algorithm is spot on and exact. So I think that is this is the method that Huang Yu used a couple of years ago in his routine. So let's wrap up. We defined some evaluation criteria, pointed to perhaps a few others, and I'm going to hop on this horse again. That simulation has long been a staple of IRT research, but it's often the case that better analytical alternatives are available. I would like to start a journal titled "The Journal of Needless Simulation," that shows that in a wide variety, that there are few situations involving conventional tests or sort of combinations of conventional tests, which is what an MST is, conventional tests connected by logic, that require simulation. Now, an item adaptive test, that's another animal. It's a cat, I guess. In that the simulation may be the the only viable approach there. But with that exception, there is an awful lot that can be done analytically, largely or often through the Lord Wingurski recursion. So that for conventional, I just said my final conclusion that the analytical approach, Lord Wingurski recursion, is a clearly superior approach to simulation in those cases. Well, thank you. I guess I'll cede control back to Duan
Thank you
Li.
very much, April, Rick, Paul, and Tim for your great presentations. Let's open it to our audience. Do you have any questions? You can type it in the chat room. I see Rick has a couple of comments.
Well, Rick is on the Lord Wingurski recursion team. So
Yeah, I was recruited years ago by Tim. So yeah, I'm a big fan. So yeah.
so between Rick and I, we've got the rest of the world to bring on board.
Any comments? We had 65 participants.
Which is more than I've ever had to an NCME presentation.
Exactly, yeah. We still have 2 minutes.
Well, I could talk more about some of the things that Hong-Yu Lim found a few years
Yes.
ago. This sort of fits in with April's presentation. Is that well, one of the reasons that the GRE went to the 1-3 design is they found that the diminishing returns beyond that were so steep that it was really not worth it. In that the other thing they found that was surprising, and I think that Huang Yu's research also confirmed, is that under the 1-3 things are surprisingly, again, robust. In that a 1-3 with about half the items in either half works pretty well. That there are arguments, I guess theoretical arguments in favor of front loading the items and making a good decision versus back loading the items and doing better targeting. Again, the GRE folks found that it didn't much matter. The going beyond 3 levels in the second stage sort of didn't contribute much, in that some of those levels almost went completely unused. So that well, anyhow, that's how the GRE ended up where it was. Is that a lot of those design considerations were not terribly consequential.
And Huang-Ju posted a link in the chat room about the research he and Tim did.
Oh, good.
About posting the online, I think NCME is doing, yes. They have a recording, so I'm sure they will send a link to the recording after the session. And then we can share that link and video for those who cannot attend this session.
Well, ordinarily, this is about when I would be heading to the hotel bar.
Well, I
hate
think
to drink alone, though.
Do we have any questions, comments, suggestions, and sharing of any research results? If not, I think we're just about the time. Let's thank our presenters again, and thank you very much for your nice presentations, and thank you to the audience for your interest to join us at this time. Thank you.
Thank you, Duan.